System analysis and control engineering answer one practical question. If I push on a system, how does it move, heat up, spin, settle, oscillate, or fail? In this video, the map is model, analyze, control, and validate. We will keep the mathematics close to engineering meaning, so every equation has a job, and every diagram tells us what to test. A system starts as an input-output idea. An input U of t enters a block, the system transforms it, and an output Y of t comes out. Throttle becomes speed, electrical power becomes temperature, and force becomes position. Before doing math, choose the boundary. What is inside the block, what is outside, and which output matters for the design. The first useful approximation is often linear time invariant. Linear means superposition, scaling and adding input scales and adds responses. Time invariant means the rules are the same if we start later. Real machines are not perfectly linear, but near an operating point, many systems are close enough that this local map becomes a powerful engineering tool. Now build a model from physics. In a mass, spring, and damper, force pushes the mass, the spring pulls back with stiffness K, and the damper resists velocity with coefficient B. Newton's law gives mx double dot plus bx dot plus kx equals f of t. Inertia, damping, stiffness, input, and output are all visible in one equation. The same mathematical shape appears in different domains. Mechanical systems use mass, damping, and stiffness. Electrical circuits use resistance, capacitance, and inductance. Thermal systems use heat capacity and heat loss. Rotational systems use inertia and friction. This is why control theory transfers so well between motors, ovens, vehicles, and circuits. The Laplace transform turns differential equations into algebra in the S domain. A derivative becomes multiplication by S. Once initial conditions are treated separately, that turns mx double dot plus bx dot plus kx equals f into ms squared plus bs plus k times x equals f. The reward is that natural modes become easier to see. The transfer function is the ratio from input to output in this domain. For the mass, spring, and damper, x of s over f of s equals 1 over ms squared plus bs plus k. The denominator gives the characteristic equation. Its roots are the poles, and those poles are the first big clue about the system's behavior. Poles make stability geometric. In continuous time, poles in the left half of the complex plane decay. Poles on the imaginary axis oscillate without decay in the ideal model. Poles in the right half plane grow. So the complex plane becomes an engineering map. Left is stable, right is unstable, and distance from the axis affects speed. Eigenvalues are the state space version of poles. For the autonomous system x dot equals ax, a special direction v is an eigenvector if av equals lambda v. Along that direction, the motion grows, decays, or rotates according to the eigenvalue lambda. The eigenvectors are modal directions. The eigenvalues are modal rates. For a mass spring damper, the undamped natural frequency is omega n equals square root of k over m. It is the frequency the system wants to use when energy trades between mass and spring. Damping changes the observed oscillation to the damped natural frequency. That is why eigenfrequency is not just vocabulary. It predicts ringing. A first-order system has one pole and one dominant timescale. Its standard form is k over tau s plus 1. The gain k tells the final change, and tau is the time constant. After 1 tau, a step response has reached about 63% of the way. After 4 or 5 tau, it is practically settled. A room heater is a first-order intuition pump. The room temperature does not jump when power is applied. Heat capacity stores energy, heat loss removes energy, and temperature approaches equilibrium gradually. If you make the controller impatient compared with the room's time constant, the controller will fight physics instead of using it. A second-order system has 2 poles, usually described by natural frequency omega n and damping ratio zeta. Low damping rings and overshoots. Moderate damping can be quick and clean. Heavy damping is stable but slow. This is the classic transient response language. Rise time, overshoot, peak time, and settling time. Zeros shape the way inputs excite the modes. Poles describe the system's natural behavior, but zeros can amplify parts of the response, reduce others, or even create undershoot if a zero is in the right half plane. That is why two systems with similar poles can still respond differently to the same command. State space names the internal variables directly. Instead of only asking for input and output, we write x dot equals ax plus bu and y equals cx plus du. The vector x is the state, enough information to predict the future when the input is known. For the mass spring damper, position and velocity are natural states. Transfer functions and state space are two views of the same dynamics. Transfer functions are compact for single input, single output work. Each space is better for multiple states, multiple sensors, multiple actuators, observers, and computation. The key bridge is that poles of the transfer function match eigenvalues of A, except for special cancellations. Now add feedback. Open loop control sends a command and hopes the plant follows. Closed loop control measures the output, subtracts it from the reference, and acts on the error. That subtraction junction is the heart of control engineering. The system becomes aware of its own mistake. With unity feedback, the closed loop transfer function is C of S over 1 plus C of S over 1 plus C of S. The denominator 1 plus Cg is the new characteristic equation. This is the central point. Feedback does not merely correct the final output. It moves poles and changes the dynamics. Feedback is useful because models are imperfect and disturbances exist. A hill slows a car. A window cools a room. A load torque slows a motor. Feedback uses measurement to fight those uncertainties, but it is not free. Gain can improve accuracy and speed, while also increasing overshoot, noise sensitivity, actuator effort, and instability risk. PD control is the most common first controller family. Proportional action reacts to present error. Integral action accumulates past error and removes steady offset. Derivative action reacts to the trend and can add damping, but it also amplifies noise. The three terms form a practical language for shaping many ordinary feedback loops. For motor speed control, the plant has inertia and friction. A voltage command gradually changes angular speed. Proportional control may leave a small speed error under load, because small error gives small push. Add integral action, and the accumulated error keeps pushing until the measured speed reaches the reference. Cruise control is the same feedback story in a vehicle. The reference is desired speed, the measurement is actual speed, and the controller adjusts throttle. Hills and wind are disturbances. The design is not only about tracking a number. It must also respect comfort, actuator limits, engine delay, fuel use, and safety. Thermal control shows why faster is not always better. A room, oven, or incubator can keep heating after power changes because energy is stored in the plant. Integral action removes offset, but aggressive gains can create slow overshoot. For slow plants, respecting the time constant is often the smartest control move. Root locus asks where the closed-loop poles move as gain changes. Start at open-loop poles and increase K. If the branches move left, the response tends to become faster. If they move toward the imaginary axis, oscillation grows. If they cross into the right half plane, the closed loop becomes unstable. Frequency response asks how the system handles sinusoidal inputs. The Bode magnitude plot shows gain versus frequency, and the phase plot shows lag versus frequency. Low-frequency loop gain helps tracking and disturbance rejection. High-frequency gain can amplify noise. Phase lag limits how aggressive feedback can be. Margins convert frequency response into robustness language. Gain margin says how much more gain the loop can tolerate before instability. Phase margin says how much extra lag the loop can tolerate. A simulation with no margins is fragile because the real plant will never match the model exactly. Steady state error connects references, disturbances, and low frequency loop gain. A type 0 loop can have finite error to a step. Adding an integrator increases low frequency gain and can remove that step error. The trade-off is familiar now. Accuracy improves, but phase lag and overshoot risk can increase. Controllability asks whether the inputs can move the internal state where we need it to go. Observability asks whether the measurements contain enough information to reconstruct the state. A system can have elegant equations and still be a poor control problem if the actuator sensor is placed badly. The inverted pendulum makes eigenvalues physical. Hanging down is naturally stable. Balanced upward is naturally unstable. Feedback measures angle and angular velocity. then moves the base so the unstable mode is pushed back into stable behavior. In state space language, the controller changes the closed-loop eigenvalues. The practical workflow is iterative. Define the goal, choose inputs and outputs, build a physics or data model, linearize if needed, analyze modes and responses, design the controller, simulate disturbances and limits, test carefully, and update the model when reality disagrees. The loop matters as much as the equations. Beyond this first layer are lead-lag compensators, state feedback, observers, Kalman filters, LQR, H-infinity control, model predictive control,